This is your second lesson that deals with imaginary, but it's imaginary and complex numbers. So recall that we had imaginary numbers in our previous lesson, and they would be written in the form of bi, where b is a real number, and I is the imaginary unit that's defined by that I squared equals -1, which also kind of means that I equals the square root of -1. So you can think of this that this is actually a radical, that this is a number like 3 times the square root of -1. So it's in some ways treated no differently than any other problem that we've dealt with radicals, that I is just a type of radical. Well, there's another type of number called a complex number, and it utilizes the imaginary number, but we add another real number to it. So it's always in this form, and it's written as a plus bi, and that's the accepted format throughout the United States textbooks and testing and everything else, is that a complex number is written in the form of a plus bi. A is a real number, b is a real number, and I is the imaginary unit. Remember that the imaginary number is both b times I, not just the I, and it's not just the b, it's the bi is the imaginary number. Now here's some examples of some complex numbers. I've got 3 plus 7i. 3 is the real, but they call it the real part, and 7i is the imaginary part. Here's another one where -2 plus I, and -2 is the real part. I, that's 1i. We don't see that, just like when we talk about x, we don't write 1x, we don't write 1i. It's just I means 1i, and that's the imaginary part. Here I've got 5 minus 8i. 5 is the real part, and -8i, that minus goes with it, so -8i is the imaginary part. And here we've got -12i. Well, it doesn't have an a. Well, the real part is 0, because remember 0 is a number, so there's a 0 there, and that's the real part, and -12i is the imaginary part. Well, here's one more. 9. You say, well, there's no imaginary part. Well, remember, that's 9 is the real part, plus 0 times I. That's the imaginary part. So if you think about it, all real numbers can be written or be considered complex numbers. It's just that the b is a 0. So you pick any real number and you can say that it is part of the complex number system. Let's look at some operations we can do with these complex numbers. Now that we're going to be dealing with a plus bi, and realize that every single number that we know in the entire universe now can be written, the ones that we've discussed up to this point, can be written as a complex number. So we're going to talk about how we add and subtract complex numbers. Well, the idea is addition and subtraction, which it always has been, is just collecting like terms. And remember that we have a real part and we have an imaginary part. So reals are going to get added with reals, and the imaginaries are going to get added with imaginary, or subtracted. So we're either going to subtract our reals and subtract our imaginary, or we're going to add our reals and add our imaginaries, depending on the problem. So in the first problem, we've got these two complex numbers, 8 plus 7i, and we have the number -3 plus 4i. Those are just two numbers. They got lots of parts to them, but it's just two numbers. And I'm adding those two numbers. To add those two numbers, I'm going to add reals with reals. So I'm going to add 8 plus -3, and I'm going to add the imaginaries, 7i plus 4i. Well, 8 plus -3 is 5, and 7i plus 4i is 11i. So I have 5 and 11i. And this is the one complex number. That is one number. Even though you see a 5, you say, oh, it's got the number 5 and the number 11. It's one number. It's 5 plus 11i. Here we have two more complex numbers, 5i minus 3, and we're going to subtract the second number, 2 minus I. So we are going to subtract the parts. That's what we're doing here, subtracting them. So I'm going to have, looking for my reals. Ooh, that first number is written in a different order, 5i minus 3. Where's the real? It's -3. Even though it's written in bad form. It should have the real first, but sometimes you're given, especially in textbooks or on quizzes, things are not in their proper order, so you have to identify and make sure you get the right order. So negative 3 and 2, and we're going to subtract that. So negative 3 minus 2, because that's what we are subtracting. We are subtracting their parts. And I have a plus sign here because we're not subtracting the number, we're subtracting the parts of the number. I'm subtracting reals, so negative 3 minus 2. And I'm going to subtract, I'm going to now subtract the imaginaries. 5i minus negative I. And the negative of a negative, subtracting a negative means to add. So I'm going to have negative 3 minus 2, which is negative 5, and I'm going to have 6i. That is the final answer. Negative 5 plus 6i is the one and only complex number for the solution to that problem. Let's look at multiplication of complex numbers. It's really a distribution problem. Well, I'm going to show you two different methods. The distribution is the way the textbook typically shows it. And it's very similar to that of binomials. You're going to multiply 3 times 4, and I'm going to multiply my two reals, so I get 3 times 4, and then I'm going to multiply my two imaginaries. And I always like to do when I do the distribution, so we're not really following the FOIL method. I'm doing the first and I'm doing the last. So 3 times 4 is 12, and I'm going to do 2i times I, which is 2i squared. Then I'm going to do my outsides, my one real and one imaginary, 3 times I, which is 3i. And I'm going to do the other pair that is a real times an imaginary, which is going to give me 8i. And now I look at what I have here. And I notice that I've got I squared. I squared is negative 1. Since I squared is negative 1, it's 2 times negative 1, which is negative 2. So 2i squared is actually the number negative 2. So what I have is 12 minus 2, which is going to be 10. And then I can add the 3i and the 8i, and I get 11i, and that's the final answer. Now this distribution method, multiplying the first, the 3 and the 4, and then the 2i times the I, and then etc., that's the way the textbook's going to show you typically. I prefer the stacking method. And I showed you that with radicals because specifically for when we deal with complex multiplication. So I stacked them, and here's two different two different complex numbers that I am going to multiply. So I've got 6 plus 9i, and the other number is 4 minus 5i. And I stack one on top of the other, which is similar to what we do with regular old, numeric multiplication, 23 times 47. We write it in stacking. We don't write it linearly. And I'm going to multiply straight down. I showed you this with radicals. I'm going to do the same thing. 6 times 4, and I get 24. And then I'm going to multiply straight down again, 9i times negative 5i, and I'm going to get negative 45i squared. And then, after I do the straight down, I'm going to do the diagonal, 4 times 9i, and I'm going to write it over on the left here. 4 times 9i is positive 36i. Make sure you write the sign, positive 36, or negative, whatever it would be. Positive 36i. Then I'm going to do the other diagonal, 6 times negative 5i, and get negative 30i. Before I collect, I have to look at the numbers I have here, and I notice that, I've got I squared, which is a negative 1, and I have a negative 45. So if I had a negative 45 times negative 1, it's actually going to become positive 45. The I squared goes away. Notice how when I multiplied straight down this, and I did in blue, I ended up getting 24 plus 45, not imaginary numbers. That's why I wrote them in blue, because remember I keep writing all the blue things in those are my reals. When I multiply straight down, I will always get real numbers. As long as you are stacking this in the order of reals over reals and imaginary over imaginary, when you multiply straight down, you will only get real number products. Now I can collect everything, and I collect those blues, those reals. 24 plus 45 is 69. I collect my imaginaries, and I get plus 6i, and that's my final answer. Because the stacking method is a little bit new, let's do a few more stacking method problems so you can see them, and I'm going to go through them a little bit faster. So I've got 2 plus 11i times negative 2 plus 8i. I stack them and I put that little L-shaped thing. I go straight down, negative 4. I get 11 times 8, both of those i's, so I get positive 88i squared. But I squared is negative 1, and so I can change that to a negative, and so it becomes negative 4 minus 88. Now I do the diagonals, negative 2 times 11i, negative 22i. 2 times 8i, I get positive 16i. I'm now going to collect a negative 4 and negative 88. I get negative 92, and negative 22i and positive 16i is negative 6i, the final answer. Another stacking method, another example. 13 minus 9i, negative 2 plus 2i with a little L shape. Straight down, 13 times negative 2 is negative 26. Negative 9i times positive 2i would be negative 18i squared, but that I squared makes it positive 18. Doing the diagonal, negative 2 times negative 9i is positive 18i. 13 times positive 2i, 13 times positive 2 is positive 26i. Collecting like terms, I get negative 8 plus 44i, and that's the final answer. We have 2 more examples to go through. 7 plus 3i times 6 plus 10i with a little L shape. Straight down, 42. Now, right there, negative 30. 3i times 10i. How did I get that? Remember that to get the negative 30, I did positive 30i squared, which is negative 30. From now on, I'm not going to even write the I squared. I'm just going to do the multiplication and then change the sign for the I squared. So I get a diagonal of 6 times 3i is positive 18i, 7 times 10i is positive 10i. Collecting like terms, I get 12 plus 88i, and there it is. And the last example, 5 plus 2i times 5 minus 2i. That's an interesting example. There's something about those numbers, and we'll talk about that in a few moments here. I'm going to multiply those. Straight down, I get 25. I would get negative 2i squared, which means I'm going to get positive 4. Diagonal going upwards, I 5 times positive 2i is positive 10i. The other diagonal is negative 10i. Positive 10i, negative 10i. That's going to be 29 plus 0, which is just 29, which is my final answer, which is rather interesting because we started by multiplying these complex numbers. And this 29 is just a simple real number. There's no i's left in that. Well, what were we multiplying? What was this 5 plus 2i times 5 minus 2i? That was the conjugate pair. And if you remember with radicals, when you multiply conjugate pairs, you eliminate the radical. In complex numbers, the I is the radical. It's the square root of negative 1. So when you multiply conjugate pairs of complex numbers, you're going to always get a real number because you will have eliminated the i's. And that is the end of more problems with complex numbers.